So Vojislav, you're welcome to present.
Thank you, Misha, and thank you for the opportunity to be here and to present uh, my current work and my plans for my future work at ITMO, hopefully. So, can you just to check? Can you see my screen?
Yes, we can.
Okay, perfect. My presentation has two parts. First, I will give introduction to time-varying metamaterials and metasurfaces, and then I will present the plans for a project which I have been participating and the current work which has been done. And to begin with metamaterials, I believe they don't need special introduction now because they have been a very big research area during last 20 years. And I think it will suffice to say they're artificial composite materials with engineered properties. And metasurfaces represent planar analog of metamaterials or 2D surfaces with sub-wavelength resonant inclusions, which have the benefits of reduced size, weight, easier fabrication, and reduced materials. And in principle, they can be used for full control of both reflected and transmitted fields, the basis of which is Huygens principle. And they also represent a huge research area in recent years, and they have been used for many applications, like frequency selective surfaces, transmit arrays and reflect arrays, then polarization changing metasurfaces, and to name just a few of them. And time modulation is something which is relatively new concept in the field of metamaterials and metasurfaces, which enables us to gives us an additional degree of freedom for engineering the properties of these structures, and enables some new functionalities which are not possible without this time modulation, which I will explain more about in a minute. So this is just an overview of the possible response types of metamaterial or any system in general. So most of the time we have linear systems which are here depicted as this linear type of circuit, and their most important characteristics is that the frequency in such systems is preserved. So for the response will always be on the same frequency as the excitation of the system, which allows us to analyze them in frequency domain using Fourier transform. And most of the theory and most of the practical devices which are used are usually operated in this linear regime. And also this linear type of materials and systems are usually reciprocal unless they contain some special materials like magneto-optical materials, and which I will discuss more about later. Then we have linear but time varying systems, which are represented as this circuit but with variable parameters in time. And in this case, the output frequency is not necessarily equal to the input frequency, and strictly they have to be analyzed in the time domain, not in frequency domain. And such systems can be used to realize non-reciprocal behavior. And the most important practical case is when the modulation of the parameters of the system is periodic, and then we can use the Floquet theorem to analyze the behavior of the system, and it will lead to it will lead to appearance of Floquet harmonics in the spectral response of this system. And then we also have the nonlinear system, which are general, quite general, and we can't say something in advance about non-linearity, but I just summed some uh, I here just list some of the effects in nonlinear systems which are not possible in linear type of systems. It is, and these are the bistability, multistability, then tuning and switching of response of such systems, usually as in response to the power of the incoming signal. Then the harmonic generation, like second harmonic, third harmonic, and so on. Also frequency mixing. If we have input on two different frequencies, then we can obtain a response which has any combination of any combination of those two frequencies. And they also can support parametric processes like parametric amplification and oscillation, and also nonlinear waves such as solitons. And the boundary between linear and time varying and nonlinear is not very strict, because we usually require some type of nonlinear material to realize this time variability in this type of system. And these two areas are connected uh, with the tunability. So because the linear time varying systems require tunability, and tunability is also a feature of nonlinear systems, but the tunability is a whole research area on itself. So I just indicated it here like this. And um, so about the analysis of the time varying systems which have periodic modulation. So generally, when we have they will be described by linear differential equations, but with variable parameters. And when this variation of parameters is periodic, then we can apply the Floquet theorem, which gives us the general form of the solution of such equations. And this is a general mathematical statement which is used in many areas of physics, like solid state and so on. And the statement is that the general solution of such equation will be a product of harmonic part and another function which has the same periodicity as the parameters of the equation. And this function, which is here labeled as p of t, and it can be expanded in Fourier series to obtain these Floquet harmonics, which are depicted on the right. So the point is that if we excite the system with some input frequency f0 in a response in a response spectrum, we will obtain harmonics which are spaced evenly on the distance which is equal to the modulation frequency. And another important concept for time varying systems is the concept of parametric oscillations. So in the case when we have a linear harmonic oscillator with variable parameters. In this case, it is shown, the equation is shown without damping term, but if it includes damping, then it can be reduced to the same form with the change of variables. And the simple example of this parametric oscillations is a child on a swing on a playing card, shown on the right. So by periodically squatting and standing, the amplitude of the oscillations of the swing can be increased and maintained. And mathematically, the simplest case of this parametric oscillation is in the case when the pump frequency, which is the frequency of the parameter change, is equal to two times the frequency of the signal. And in that case, depending on the phase difference between signal and pump, the oscillations can be attenuated or amplified. And this concept has a long history in particular in microwave engineering, where it was used for parametric amplifiers. Which are the main benefit of which is that they have very low noise compared to the negative resistance amplifiers like in transistors, and they have historically been used for low noise applications like space communications and so on. And the reason for this low noise is because in this case, the reactance is varied in the system, which produces no noise as opposed to resistance. And recently, however, it attracted the attention of researchers that this parametric process can be used not only for amplification, but also to produce non-reciprocal response. And about fundamental concept in physics, which is related to the time reversal symmetry. In the electromagnetic case, it's the time reversal symmetry of Maxwell's equations. So it's formulated as this equality of these reactions in the case of interchanging the source and the observing point of the electromagnetic field, and in the case of scattering parameters is that this scattering matrix of a reciprocal system is equal to, to itself transposed. So the S12 is equal to S21, or the transmission in the both the directions through a system is equal. But there are many applications which require non-reciprocity, which basically require one-way propagation, and most notably in communication systems like radars and transceivers. It's required to separate the uplink and downlink, or the transmitted and received signal, and also it's required to separate some to protect some sensitive components from interference and from reflections, which can be caused by mismatch and so on. And traditionally in microwave engineering, it's this non-reciprocity is achieved with magneto-optical materials such as ferrites. And the basis of this effect is that they have the electric constant, which depends on the bias magnetic field, and this magnetic field, external magnetic field, breaks the time reversal symmetry of Maxwell's equations, and they have been used to build devices like circulators and isolators, which allow shown on the picture, right, which allow propagation only from port 1 to port 2, from port 2 to port 3, and so on, and isolators which allow propagation only in one direction. But these magneto-optical materials have many drawbacks, because they are bulky and heavy, and they can't be used with integrated technologies like in integrated circuits, and also they work only on lower microwave frequencies, because on optical frequencies this magneto-optical effect is very weak. And so the idea of many researchers, and which has been published already in many papers, is to use time modulation to obtain non-reciprocity. So there are two main ways how this is done. The first one is shown on the left, and it's so-called traveling wave modulation, where the dielectric constant of the medium is modulated with a plane wave like dependence of permittivity, and in this case it will produce the breaking of the time reversal symmetry. And on this example, it shows a waveguide which has two modes, and due to this traveling wave modulation, it will produce the coupling between the two modes, but the coupling will be oblique uh, on the wave diagram, so it will only produce strong coupling for the wave propagating in one direction, while the coupling between the two modes would be very weak for the wave propagating in the opposite direction. So this effect can be used to construct the waveguide, which allows uh, only unidirectional propagation. And the similar idea is based on so-called artificial angular momentum, where this type of ring resonator can be again can have sort of plane wave like modulation, but in circular form around this ring, and it will cause the lifting of the degeneracy of the two modes which exist on the ring. So it will produce different resonances for the different directions of of the traveling wave along the circumference of the ring. So it will uh, it allows us to create filters which have frequency difference from for different for opposite propagations. And in the case of metasurfaces, this traveling wave modulation can be used also to achieve non-reciprocity in reflection or in transmission. And here I picked one example of the paper, and there are many more. But this was interesting because it shows how a single metasurface can be used to realize many functionalities depending on the modulation parameters. So it can be used to realize isolator, quasi-isolator, non-reciprocal phase shifts, and circulator behavior by distributing the energy of the incoming wave in different diffraction orders, and also depending on the direction of the propagation. And now moving on to the proposal of the project. Typically, the non-reciprocity to realize non-reciprocity will require at least two independently modulated elements, and in some cases many more. And it is very difficult to realize such modulation in practice because it requires biasing circuits, which would be extremely complicated. And in normal isotropic systems, it's not possible to realize non-reciprocity with only single uniform time modulation. But in the case of bianisotropic media, which are characterized by coupling between, so the electric polarization is not function only of electric field, but also of magnetic field and vice versa. And it has been shown theoretically that in such media, it is possible to obtain non-reciprocity using only uniform time modulation. And here on the right, a unit cell of such bianisotropic metasurface is shown, and it's characterized by this asymmetric impedance, because in the were the metasurface not bianisotropic, then the Z1 would have to be equal to Z2 in this equivalent circuit T cell of the metasurface. And in this case, it has been shown that it is possible to achieve reciprocity only capacitance and uniform modulation of capacitance across the whole metasurface. And the results the results below show that it can be operated in several regimes, so it can provide also gain if necessary or attenuation, but there is significant difference for forward and backward propagation. So our research plan, which I started working on with the colleagues from ITMO and from other universities, is to create to fabricate this metasurface and to characterize it experimentally. So our plan consists of four basic steps. The first is to develop numerical simulation methods of these time modulated metasurfaces, because normally simulators, typical electromagnetic simulators, uh, allow only linear time invariant materials. So our plan for this is to use combination of 3D electromagnetic analysis and nonlinear circuit analysis, which may be some time domain simulator like SPICE or harmonic balance simulator. And we wanted to first manufacture a low frequency prototype of the unit cell of this metasurface, because we can simulate the propagation of on a metasurface with just a single unit cell, which is connected with transmission lines to some transmitter and receiver. and to implement this varying capacitance with the help of Varactor diode. Then after this confirmation, the next step would be to design the actual metasurface. This requires extensive work on study how to integrate the Varactor diodes and how to provide bias. And then finally to implement the designed metasurface and with sufficient number of unit cells, and to characterize it experimentally by measurements in anechoic chamber, and to confirm this theoretical proposal. We are at the points 1 and 2 of this plan, and we are now trying to make this low frequency prototype. And I will just more about it a little bit later, but just to mention some general properties of the Varactor diodes. So they are Varactor diodes are actually voltage control capacitance, and the basis of operation is that they are operated in reverse bias when there is a depletion layer on the PN junction, and the thickness of the which is related to the capacitance is can be controlled by the voltage of the reverse bias on the diode. And this is generally this is inversely proportional to the square root of the voltage. And also there is in addition to this capacitance, the equivalent circuit of the Varactor diode has a series resistance with the consequence of resistance option, and this is the main limit in the high frequency operation of the Varactor diodes. And here on the right shows a typical capacitance voltage curve of a Varactor diode, which we thought was suitable for this this experiment. And so how to model this Varactor diode when it's when modulated periodically. So in this case, the pump frequency is equal to 2 times the signal frequency, and we can expand the capacitances and the voltages and currents in Fourier series. So we can expand them in these Floquet harmonics, which I mentioned, and in the simplest approximation, we can retain only the 0 harmonic and the -1. Because this is relatively crude approximation, but it's useful to understand the operation of this diode. So in this degenerate case, when the pump frequency is equal to 2 times the signal frequency, this -1 and 0 frequency will actually, and the admittance of the diode is described by this expression on the right. So it has it has the mean capacitance part, which acts as a capacitance, and also the first harmonic, which is multiplied by this phase factor, which is the phase between the signal and the pump. And depending on this phase difference, it can act as capacitance or resistance, and it can be also positive and negative resistance. So this is depicted on these graphs. So this is the possible admittance and impedance of this Varactor diode as a function of phase difference between the signal and the pump for the values which are extracted from the simulations based on the model of the diode. So we can see that we can obtain negative resistance of this diode, which is the basis of the parametric amplification, and also the basis of this non-reciprocity in this type of the circuit. And we have this mean capacitance, which usually has to be cancelled by the rest of the circuit, so that we can operate the diode purely as a negative resistance. So here is the proposal of the low frequency circuit, which was planned at 100 megahertz to realize this concept, and it includes the Varactor diode with bias, DC bias, and then the pump, which takes the part of the incoming signal and doubles the frequency uh, gives it appropriate phase shift and amplification, and then it's used to modulate the diode, to pump the Varactor diode. And we also need the matching, because we need to cancel this mean capacitance of the diode, and also to transform the resistance to the suitable value. And then we have also filters to suppress the pump harmonics. Uh, and also this inductance, which simulates the bianisotropic metasurface. And uh, yes, so this type of circuit can be connected to a network analyzer or some other detector, and it can be used to measure the non-reciprocity. So the difference in the propagation in different directions. Here is the schematic view of this proposed experiment. So the plan is to produce the PCB, which will host Varactor diodes, biasing circuit, and matching circuit, and this inductance on a single PCB, and then to provide a pumping circuit, to realize pumping circuit on another PCB, which will allow us to switch the input and output between the ports. And the important point here is that the phase difference of the phase shifter needs to be the same in both directions, because this should simulate the realistic metasurface. And this design has been confirmed by simulations. So in simulations, we obtained a significant difference between forward and reverse transmissions. It is about almost 30 dB difference between the levels of signal in transmission, in the transmission in forward and reverse directions. And currently we have ordered the components. We have ordered the components for this experiment, and we are currently waiting for their delivery to proceed with the fabrication of this circuit. Unfortunately, it's taking a lot more time than it normally should, which is which is due to the current situation. And so I will also want to share my view of my potential stay at ITMO. Uh, the main goal is to produce fabricate this metasurface surface, which allows fast capacitance modulation in the range of about 10 gigahertz or even above. And and this will allow us to test new theoretical concepts, most notably this non-reciprocity with uniform time modulation in bianisotropic metasurfaces. But not only that, because this field of time modulated metamaterials with very fast time modulation is something which I feel is has really rich opportunities for new theoretical concepts, because most of the current theory is based on a time invariant system. So there are some really exciting possibilities with this fast time modulation. So there are some papers which suggest that it's necessary to revisit some fundamental concepts in electromagnetics, like the dipole polarizability in the cases when there is this really fast time modulation. And then also this type of metasurface will allow us to develop some advanced new functionalities which are not possible otherwise with time invariant metasurfaces and potential applications, and most notably the non-reciprocity, which is very important application for many fields, like communications, sensing, radars, and so on. And so I believe this work will be very rich for opportunities for collaboration with both academic and commercial partners. And I would also like to this idea also, which have been helping in realization of this project. And with this, I would like to conclude. So I believe that time modulated metamaterials and metasurfaces are relatively new research field, which has interesting new physics and also enables new functionalities which are not possible otherwise. And the proposed metasurface would be the first realization of non-reciprocity with uniform time modulation. And in general, it would be one of the first realizations of non-reciprocity with time modulation in general, because most of the published papers are theoretical only, because the realization of such structures is very difficult. And also, as I said, I believe it would provide a platform which would allow us to study further concepts and applications. And with this, I would like to thank you for the attention.
Okay, thank you, Vojislav. That was an interesting talk. Do you have any questions in the audience? Yeah, Stas?
Hi, Vojislav. Thank you so much for your update. Very interesting. So I have a question. Maybe I have two questions. So one is technical and another one is general.
Okay.
So maybe the first one is shorter, then I'll start with this. So in your model that you use to characterize this transmission for both directions, did you consider some realistic parameters of the diodes, some parasitic elements that can be included into its equivalent circuit, or it was just characterized by some capacitance and resistance? That was the first one.
Okay, so yes, in my simulations, I use the SPICE model for the diode, and also which includes all the parasitics of the packaging. But this first experiment is at 100 megahertz, so these effects are not so important.
Okay, so anyway, we can be sure that we should see the same behavior in the experiment already. So if everything is included.
Yes, it includes the parasitic inductance and the parasitic capacitance of the packaging.
Okay, I see. And another question is for stability. So since it is anyway an active element and you generate some energy due to the pump, can it be checked to be stable using this model, or you need some additional model to do that?
Well, I think this model should account for the stability. So this is I mean, in this case, you don't have some feedback in this system, so it's not. It's basically not possible to have positive feedback and to have some instability in this way.
So we don't even have to check it in this case, because as far as I know, for non-Foster element, for example, people try to investigate the instability effects, and even due to some, let's say, parasitic coupling between different parts of the circuit, through electromagnetic waves or through some signals that are induced on one conductor from another one, then some parasitic feedback may still occur.
So yeah, that is a good point. Yes, that's a good point. But yes, I didn't check it, to be honest.
It may be just interesting to look how physically this kind of circuits are done in the literature for this microwave amplifier or low frequency amplifiers. So how they visually look like maybe they should be soldered and locked in a special metal case or something like this. So do people do any special measures to protect it?
Well, at this low frequency, it's in this low frequency, it definitely shouldn't be an issue. On 100 megahertz, I think the some parasitic coupling would be very, very small.
Oh, okay.
But yes, that's something we need to check when for the next step when we try to move to the higher frequencies.
Okay, and also I have a very general question. So regarding this topic as a research direction for, let's say, a couple of years, how do you think what would be the most interesting next step to make something new, to make some new research in time variable metamaterials? Just for you personally.
Well, I think so maybe I'm just I'm not completely sure about what I'm saying now because I haven't done much research into that, but I think it would be very interesting to try to realize some of the non-linear effects or the effects which are exclusive for non-linear materials in this time varying metamaterials. So maybe things like some solitons and some other nonlinear waves, and I think it would be very interesting to see if they can be produced in this type of structures.
Okay, thank you so much. Very interesting.
You're welcome.
Okay, we have a question from Polina too.
Hi, Voya. I hope you are going well, so I'm glad to see you. Look, I have a question regarding this approach. Your experiment is now set for the megahertz frequency band, as I understand.
Yes.
Okay. I just wonder, would it be any fundamental limitation when you would like to scale to the microwave and millimeter frequency band because of the probably the Varactor diodes there operates on the different principles or something like that, or any fundamental limitation or some limitation for fabrication of the Varactor diodes over there?
So for the Varactor diode, the main limit is the resistance of the PN junction, because this is the fundamental limit which cannot be mitigated. But there are Varactor diodes which are used in this range which we plan to work on. So in the 10-20 gigahertz, there are. I mean, I have seen in the literature that people use Varactor diodes for the parametric amplifiers in this range. So I don't think that there is a fundamental limitation, but of course, to fabricate anything in this range will be much more difficult due to the various parasitics and due to more precise manufacturing, which we will need to use, and so on.
Okay, and the next question is probably the continuation of the Stas' second question. So you told that you can probably find some new physical phenomena, non-linear phenomena in such type of the metasurfaces. But could you give more understanding or give more details for the application of this phenomena in the desired frequency band?
Well, to be honest, this is just something which I have been thinking about, but I didn't do any research about that. But I assume if you could, for instance, if you could support solitons in such structures, they would be interesting. It could be interesting for some maybe even antennas and as a way to control diffraction, for instance, and in communication systems, I guess. So you could, for instance, limit the diffraction.
Okay, thank you. Yeah, I don't have any questions.
Okay, thank you, Polina. Do you have any questions from the audience on the faculty? No, I don't see anyone. I had a small question about the part where you described the general modulation in the waveguides, and you didn't say how is this modulation achieved in there.
So you mean this one?
Yeah. Is it achieved with some ferroelectricity elements? So could this modulation be achieved in, say, natural materials, not metamaterials, but some natural things?
So these pictures I took from this paper, which is on the bottom, shown on the bottom of this slide. But I think it's theoretical work only, so it doesn't give a way how to realize this. It's just a theoretical prediction.
Okay. Okay, so I don't see any more questions. So thank you, Vojislav.